Last but not least, let's use our water analogy to analyze voltage drops in parallel circuits. So what we have here is our parallel circuits. We've got these gravel-filled pipes right here, and we've got our pump, which is pumping it up to 20 psi on top here, and gets back to 0 psi right there. So what we have for these parts are frictionless pipes. So if it's frictionless, it loses no pressure. So right here, way over here, it's still 20 psi. We haven't lost any pressure. Right here, it's still 20 psi. We haven't lost any pressure. Right here, it's still 20 psi. We haven't lost any pressure. Similarly, down here, for this whole part down here, we are assuming that that is all 0 psi, 0 psi here, 0 psi here. The pressure's back down to 0 all through this, and we're assuming that it can just coast without any friction back into our pump. So what is the voltage drop across, or the pressure drop across each one of these gravel-filled pipes? Well, that should be obvious. The delta P for all these is negative 20 psi. Delta P for this one, negative 20 psi. Same thing for this last one. Delta P across this one is just negative 20 psi. There's the same pressure difference between every one of these points and every one of these points. In other words, the pressure drop is the same when you have these pipes in parallel. Similarly, in our actual circuit here, the delta V's are going to be the same. For this resistor right here, delta V across this one, delta V is equal to negative 20. Delta V is equal to negative 20 volts. And then delta V is equal to negative 20 volts for this one too. The voltage drop from here to there, here to there, and here to there is the same for all three of these. The voltage drop across each individual resistor wired in parallel is the same. And it's equal to delta V total, which is the voltage drop across the power supply. And that's only true if it's a pure parallel circuit. It's not combined with other series circuits or anything like that. Now, the current through each individual resistor wired in parallel, we can find I1 using Ohm's law, similar to what we did before. This will be delta V 1 over R1. So in this case right here, delta V across resistor 1, just going to erase this so we can just see it a little bit better. The delta V is the same as delta V total. It's 20 volts across each one of these. Delta V is 20 volts. A resistance is 4 ohms. 20 volts over 4 ohms. That is 5 amperes. So through here is 5 amps. The current through 2 is delta V 2 over R2, again using Ohm's law. And that will be, again, 20 volts is the voltage drop across it. R2 is 10 ohms. That gives us 2 amperes. Through here, there is 2 amperes. And similarly, I3 is delta V3 over R3. Notice that the subscripts are always the same, and that's going to be 20 volts. It's the same for all resistors in parallel. 20 volts divided by 2 ohms is equal to 10 amperes. What is the total current going into and out of our power supply? We just add up these branch currents. 5 amps, 2 amps, 10 amps gives us 17 amps of total current. And by the way, it is true, it is very true that I total will equal delta V total over R total. So here's something that you could try to figure out. Without using the parallel resistors equation, what is the resistance of this entire circuit? You can find R total just by doing this. Delta V total over I total. And it will work this way as well. All right, so that's some basic circuit parallel and series knowledge. Now let's move on to the more difficult stuff.